Hello everyone, welcome to CodersArts. So today in this video, we are going to discuss about the topic of data structures and algorithms, which is your last video, part 3 of the concept. So we are going to talk about firstly non-linear data structures and algorithms. In the previous video, recap of the previous video which I'd like to give you, we had seen about the linear data structures. So namely, we had seen how to perform operations on array, namely the insert operation, the deletion operation, and how to traverse each element of the array. So we have seen the concept of arrays, stacks, queues, and linked lists in the linear data structures. We have seen that linear data structures have sequential elements, or arrangement of the elements is sequential in nature. But in the non-linear data structures, we have also seen the concept of trees. So we have seen what are trees, some of the terminologies associated with trees data structures, and we have also seen the types of trees like binary trees and the traversals. Three types of traversals associated with binary trees like pre-order, in-order, and the post-order traversal. So today in this video, we are going to discuss the concept of graphs, which is a very important and wide concept of data structures and algorithms, and it comes under the non-linear data structure because there is no sequential arrangement in graphs. So we have nodes in graphs, and you have to be aware of few of the terminologies in graphs which are different from trees. So graph data structure is different from a tree data structure. You have to understand that because trees follow a hierarchical data structure. So when we see a hierarchy, as I've given you an example of the file, whenever you are arranging your folders and files into a bigger folder, that is an example of a tree. So as you see, there is a hierarchy followed where all the files are placed in subfolders of a folder. So that is an example of a tree. But on the other hand, graph example could be a recommendation engine, or a neural network, basically, when you're talking about context of deep learning. Or on the other hand, whenever you are doing knowledge, must have heard about the common term when you are searching for any keyword in the search engine. All the key terms which are very much similar to the key term entered by you in the search engine will be retrieved. So all the information retrieval engines or search engines make use of graphs. This is what I would like to explain you, that where exactly we are applying graphs in the day-to-day life. So we have recommendation engines in the graph theory, especially. If you go deeper into the graph theory, you will understand all the applications of graphs in day-to-day life. There are a variety of use cases of graph. So whenever we want to basically calculate the distance from one point to another point, over there as well, where there are various different algorithms which will come into picture, like the traveling salesman algorithm. Then you can apply the Dijkstra's algorithm, shortest path algorithm, which is nothing but the Dijkstra's algorithm, and so on. So basically the different types of graphs. So some terminologies you have to be aware of while learning about graphs is that each element of the graph is called as a node. So when you see this is an element or a vertex. So node is nothing but the vertex of a graph. It is denoted by V. So there are types of graphs like undirected graph and a directed graph. This is an example of an undirected graph, as the word says, undirected. That is, the nodes does not have any arrows in between. So there is no direction followed, no particular direction for the nodes. That is called as undirected graph, and it is represented by V comma E, a pair over here. So V is the nodes, which are also called as vertices. E are the edges between the pairs of the nodes. So basically this is how you can see here the pair of V comma E, that is one particular vertex. As you can see, V over here is all the vertices set. This is set of vertices represented by V. All the sets of edges. One edge is called as the connection between two nodes. So there is an edge between 1 to 2, but there is no edge between 2 to 5. So 1 to 2 there is an edge. It is represented by this in the set E. Then 1 comma 4 as there is an edge, 1 comma 5, and so on. So as you can see, N is the number of vertices, which are 5, and M is the number of edges, which are 6. So let us understand what are basically where graphs are used. As I've told, there are various social media networks as well. So whenever you talk about any friend network, or you send a request to a friend, or you will see suggestions or recommendations of similar friends or friends of your friend. So that is where graphs are being leveraged. Google Maps as well is one area where graphs are leveraged, graph data structure. So when you see shortest driving path from some particular point to another particular place, that is where we see graphs being utilized. Then Facebook also, which is a social media, the degree of separation between some person and the other person, the first order degree, second order friend, that is also an example where graphs are used. So as I've explained you some terminologies like V and E, what is a vertex, what is an edge. You have to also be aware of some terminologies associated with graph like U, which is a neighbor of V. So when I say an edge is equal to U comma V. So U and V, as they're in, whenever we say that U and V are neighbors of each other, or basically there is a connection between them, it is represented by an edge. So U and V can are called neighbors because there is a edge which is connecting U and V, and U is adjacent to V, which is implied by this first statement itself, and then E is incident on U and V. This can also be written as U and V are the endpoints of E. So this is some of the terminologies which are frequently used in problem statements while you're solving problems of graphs. So what is a path basically? Path is a sequence P of nodes V1, V2 and so on up to Vk minus 1 and Vk with the property that each consecutive pair Vi plus 1 is joined by an edge in E. So basically path, as you see here, there is a 1, 4, 2 is not a path over here because the sequence, which is a path, is basically a sequence, we can say, of the nodes with the property that each consecutive pair is joined by an edge E. But you see here that the consecutive pair 1, 4, 2, it is not a path because the consecutive pair is not joined by any edge in E. There is no edge, as you can see, between 1 and 2. But over here, 1, 3, 4 is also not a path. So 1, 4, 2 is a path, as there is an edge between 1 to 4 and then 4 to 2. So 1, 4, 2 is a path, but on the other hand, 1, 3, 4 is not a path. And that is because, as you see, there is no edge between 1 and 3. Although there is there is no edge between 3 and 4 as well. Although there is an edge between 1 and 4, there is no edge between 1 and 3 and 3 and 4. So hence 1, 3, 4 is not a path. So the path is always sequential in nature. It's nothing but it's a sequence of nodes. So whenever you see there is a disjoint arrangement, like 1 and 3 are not connected with each other, we cannot say that 1 and 3 are connected or they do not form any path. So what is basically distance in graph? The distance from U to V is the minimum number of edges in any path from U to V. So when you say the distance between 1, 2 is 1 and the distance between 1 and 3 is 2, because the number of edges between 1 and 3 are 2, because there is edge between 1 to 2 and there is an edge between 2 to 3. So when you add the edges, the number of edges, the total number of edges between two nodes is called as the distance. So distance from between two nodes is nothing but the number of edges which are connecting them. Now, what is basically a cycle? As the word is self-explanatory, we can say cycle is basically a loop in a graph. So when you see that there is a cyclic arrangement, we can say 1, 2, 4, 1 is a cycle. So there, the starting node and the ending node of any cycle should be the same, as you can see here. Whereas the other three examples, 1, 2, 4 and the other two, are also not forming any cycle because the starting node is not same as the ending node. So when your source node, which is called as the start vertex, your start vertex or the starting node is called as the source vertex. So when your source vertex is same as your destination vertex, that is where you form a cycle or a loop. Or say whenever you're traveling and you're starting from a particular location or a place and you again come back, you travel to some different location and again come back to your initial location or the source location from where you started, it forms a cycle. You're forming a cycle travel. You're traveling in a cycle or loop because as you can see here, a cycle is a path of all the vertices in which the vertices, this is in which V1 is equal to Vk, where k is greater than 2. So there should be at least two vertices basically, and the first k minus 1 nodes or vertices are all distinct. So there should be no repetition of k minus 1. But of course, the last one, the kth vertex, the kth node and the first node have to be same in a cycle. So what is connectivity basically in graph? When I was talking about social media, so when you see whenever you're adding anyone to your friend circle in social media, you can see there is a connection formed between you and the friend. So we can say that what is a connected graph basically? So connected graph is nothing but whenever there is an undirected graph, it is connected if for every pair of nodes u and v, there is a path between u and v. Say you're traveling a particular distance or from a particular point to another point, there exists an edge between them, the points basically, and that is because there is a path. So we can say connected graphs are those graphs in which for every pair of nodes u and v there is a path between u and v. As you can see here, 1 is connected to 2 as well, it is connected for 4 and to 5 as well, and it is also connected, it is not actually having any edge, there is no edge between 1 and 3, but it is indirectly connected because 1 is connected to 2, which in turn is connected to 3. So we can say every edge of the or basically every nodes of the graphs are connected because there exists a path between the two nodes or two vertices. So that is called as the connected graph. And basically all adjacent nodes have to be connected here. So 1, 2, 5, 4, these all are connected to each other. 1 has a connection with 5, then it has a connection with 2 as well as with 4. Similar for the, if you consider for 4, it is connected with 1, 2, and it is having a link between 2 and 1. So this is an example of a connected graph. Whereas if you see, this is a disjoint graph here. This disjoint graph is nothing but a disconnected or not a connected graph, because although there is a link between 1 and 5, there does not exist any link between these two adjacent nodes, which is 1 and 2 or 1 and 4. So that is why these are like two separate combinations of graphs. So that is why there is no link between or no connection or an edge between these two nodes 1 and 2 and so on. So that is called as a not a connected graph. As we have discussed in our previous video that what exactly are trees. Tree is also an undirected graph here. So a tree in the non-linear data structure, it's an undirected graph that is connected and does not contain a cycle. As I've told that you can have cyclic graphs as well. You can have acyclic graphs as well. These different types of graphs available. Directed, undirected, cyclic, acyclic, or cyclic directed and acyclic directed and so on. But tree is an undirected graph always. So whenever if you see that there is a directed graph, you cannot call it a tree. So because tree is always an undirected graph and it is connected, that is each and every, there exists an edge between u and v or the adjacent nodes and does not contain a cycle. So there should not be any cycle existing in the tree. So you will also be applying the different algorithms, like the algorithms available like minimum spanning tree algorithm and so on, like under minimum spanning trees. So this is a tree basically, as I've told. It's an undirected graph that is connected and does not contain a cycle. But what exactly is a minimum spanning tree? So under minimum spanning tree algorithm, there are two types, a Prim's algorithm and a Kruskal algorithm. That is where the main motto of these kinds of algorithms you will see in trees is that they will ensure that the cycle is not formed. So basically, they follow, or the main motto over there is to find the minimum route or the minimum path, which is the cheapest route, and does not such a way the arrangement that the cycle is not formed in such cases of trees. So that is the sole purpose of why we are applying such algorithms, so that there is minimum spanning tree which exists in such. So this is a tree, as you can see here, whereas this one is not a tree. The second example over here is shown. This is not a tree because although it is an undirected graph and it is connected, it is containing a cycle. So when you see there is any kind of cycle existing, 1, 2, 4, 1. This is a cycle which is here. Also 1, 2, 3, 5, 1. This is also a cycle, another cycle which is formed. So whenever you see a loop existing or a cycle existing, that kind of a graph, although it is undirected, it cannot be termed as a tree. Now, what exactly are parents, descendants, or ancestors? So trees, as you see here, they are undirected graphs. They need not, see here, this is a tree. Even this is a tree. It has a subtree over here. And this is also a tree. But what exactly are descendants and ancestors? In the previous video, as we have discussed, that every node over here, so basically you have the root node, which is the top node, then followed by your parent node or basically the child node, and the child node may or may not have another child node. So if it does not have, over here 5 is called as a leaf node because it does not have any further nodes or further child nodes. But over here 2 is called as the parent node of 4 and 3, which are its children or leaf nodes. So these are some of the terminologies you must be familiar with now. So some of the definitions I'd like to review is that you have to understand what is NM, which is nothing but edges and the number of edges and the number of vertices. Then what is the neighbor exactly? Incident, what do you mean by incident? So whenever we say that U and V are connected by a particular edge, so we say that U is incident on V. That we can say as incident. Then what is path exactly? That is what is path? Then the number, that is nothing but the number of edges. The number path is nothing but the number of nodes which exist between two vertices which are connected. Then what is exactly a distance? When and why a cycle is formed? That is when you have the source node same as your destination node. What is connected tree, and so on. So you have to understand graph traversals. This is a very important, crucial concept in DSA. So basically, when I say traversals, as I have explained you in trees, there are three types of traversals in trees. That is the pre-order traversal, the in-order traversal, and the post-order traversal. On the other hand, in graphs, we have the two types of traversals in graphs, which are depth first search traversal, which is DFS, and breadth first search traversal, which is BFS. We'll be looking into the concepts of DFS and BFS, and we'll also be implementing the same programmatically hands-on, so that you can understand how exactly a graph is created, node is created, the corresponding nodes, and also how exactly they are initialized using constructors, and then DFS and BFS is applied. One thing you have to keep in mind while understanding graph traversals is that first you have to check if the graph is connected or not. And the approach is to explore outward from arbitrary starting node S to find all nodes reachable from S, which is the connected component. You have to first check and explore the graph, so that you have to first find out whether the nodes are all reachable from the source node or not. So a graph will always have a source node and a destination node. So a destination may or may not be given to you, but a graph, when it is given to you, you will have a source node, that is to start with. So firstly, you have to first check if the graph is connected or not. And the first algorithm we'll be looking into is the breadth first search algorithm, which explores outward by distance. Now, few points you can make a note of while learning and understanding about the breadth first search algorithm is that in breadth first search algorithm, we'll be making use of the queue data structure. So when you are going to implement BFS algorithm on graphs, you have to understand that queues, which is again a linear data structure, a queue data structure is going to come handy when you are going to apply BFS. But while dealing with DFS, that is the depth first search, it uses tags. Tags is also a linear data structure. In depth first search, we are going to make use of stacks, whereas in breadth first search, the data structure you're going to implement is the queue data structure. So the breadth first search algorithm basically is in this way, as it's visually represented to you over here in the screen. So you see here, starting at A, this is the initial vertex you're going to start with. Then you're going to visit all nodes at distance 1 from A. So from A, basically all the nodes are whichever is at distance 1 from A, you're going to explore them. Now, what do you mean by distance 1? Distance 1 means the nearest nodes, or basically the most adjacent nodes or vertices from your source vertex are going to be explored. So you're not going to first explore all the far away vertices. You're going to always start with your nearest neighbors. So visit your neighboring nodes from your starting node, and then you can visit the other nodes. So once that is done, visit all nodes at distance 2 from A. Once you have visited from distance 1, then from distance 2, and so on. Now, what is distance exactly? Distance is basically the number of edges. So we can say that A to C, the distance is 1. That is a neighbor of the node, as C and B is a neighbor of A. But the distance between E is 2. A and E is 2 because it has two edges basically. The number of edges, which is 2, which is A to C is one edge and C to E is another edge. So the distance becomes 2 between A to E. Now that you have understood a basic algorithm and how exactly the approach is done in BFS or the breadth first search, you have to understand that the observations here, the core observations, and those are the L1, which is this path, consists of all nodes at distance exactly I from S. Li, it consists of all the nodes at distance exactly I from S. There is a path from S to T if and only if T appears in some layer. So you have to understand this. So basically, whenever you're talking about trees, a collection of trees will form a forest. So when you see here many of them connected together, you have to always start with your starting node, the source node, and then keep on exploring in such a way that your cost of traveling should be minimum. So you cannot always, start from A to E directly. You will always explore your neighbors first because that will have the cheapest or the least distance. So your main agenda over here should always be to optimize your algorithm, and that can be done when you are optimizing the distance or always moving in such a way or exploring the graph in such a way that the distance is minimized. Now, if we keep only the edges traversed while doing a breadth first search, we will have a tree. So that is how you can you basically the statement says that whenever you're going to traverse only the edges while doing a BFS algorithm or an implementation, you will have a tree. So basically, for example, the property of BFS tree is that let T be a BFS tree of G equal to V comma E, where V comma E, V stands for vertex and E stands for edge. And let X comma Y be an edge of G. So there is an edge between X and Y of the graph G. Then the layer of X and Y differ by at most 1. So at most 1, it can be less than 1 as well. The difference between X and Y can be either 0 or it can be 1. So when you explore layer 0 has now what exactly are layers? As you can see in this example, this is a set. So set of the nodes basically are called as layers. So when you say A is layer 0, layer 1 is B comma C comma D. So if you see here, B, C, D is forming one layer. For instance, layer 2 is E, which is a leftover node. So this is the property of that the BFS tree should follow. And over here, you're going to make a use of queues. Now, BFS, as you know, it stands for breadth first search, right? So when do you think that BFS algorithm will come into handy, or what exactly are the applications of BFS? It is basically this property you have to understand, put in simple, that it is based on traversing nodes by adding the neighbors of each node to the traversal queue starting from the root node. So when you're starting from the root node, you have to basically traverse the nodes and add the neighbors of the each node. And BFS of a graph is similar to that of a tree. So if you say for a tree or for a graph, it is similar, but with the exception, the difference over here is that for graphs may have cycles, but on the other hand, tree will not have a cycle at all. Tree is an undirected graph without having any cycle. In whereas the difference between BFS and DFS is that in contrast to depth first search, on the other hand, in BFS all neighbor nodes at a given depth are investigated before proceeding to the next level. That is one property you have to make sure that has to be followed in BFS. So to explore the connected component, add any node V for which U comma V is an edge. That is your neighboring node is explored. U is explored, but V is not. So and also, so this is all about BFS basically. And one important, we are going to also, before going into DFS, I would like to programmatically explain you how a BFS algorithm is implemented so that you can hands-on understand. And while I'm going to code over here, I recommend you to please take notes of some important concepts I'm going to going to be verbally explaining you, so that what you can understand that where the data can be stored of the graph, that which kind of data structure, be it a adjacency list or adjacency matrix. So these two are the data structures which will come handy. So basically, while coding, I'm going to also follow the steps and then going to explain you how BFS is done to explore your graph. So basically, I'm going to code in Java. This is an online Java compiler, like as we have seen in the previous video. I've coded in Java as well. So the implementation will differ only by the syntax, but definitely the concept in any programming language is the same. So once that you have understood that how BFS and DFS is applied and what are their uses, you can now code. So firstly, we are going to import java.util.star. Then for public class main. So basically, to understand step by step, you're going to first take the data for the graphs adjacency matrix or adjacency list. So whenever you have a graph, as I've shown you, for example, say that you have a graph with all these nodes. So basically, you're going to first take the data of your given graph. This is the graph which is given to you. You have to store each and every vertex in this graph, the value, into a graph's adjacency matrix or adjacency list. Now, what exactly is adjacency matrix and adjacency list? Whenever there is a connection between two vertices in the graph, that is denoted by 1. And if there is no connection, suppose A and C have a connection, In the adjacency list or the adjacency matrix, the matrix is basically, as we have seen, it is nothing but a multi-dimensional array, we can say. So it is a 2D array. A matrix is a 2D array. So you can connect wherever there is a connection between A and C, two nodes. That is denoted by 1. 1 as the element. So a matrix will have two elements only, 0 and 1. Even a list will have 0 and 1. So a connection between two edges, two vertices, a connection between two vertices is represented by the number 1. And if there is no connection between two nodes, that is represented, denoted by value 0. So once that is done, we are going to check basically we are going to, after storing the data from your graph in graphs adjacency matrix or adjacency list, basically you're going to then create a queue. As we have discussed that BFS leverages the concept of queues. So you're going to create a queue and fill it with elements, all the items basically. And then firstly start from your root node. Root node is your starting node. You're going to activate the root node. So after doing that, then you're going to slowly dequeue or basically delete. As we have seen in the queue data structure, you're going to dequeue the queue's head or the initial element, then enqueue or insert all of the queue's nearby nodes from left to right. You're going to explore left to right. So BFS basically, whenever I'm going to like to pictorially represent it. So if this is a graph, moving left to right is how BFS is done, but you're moving from top to bottom. That is where a stack comes into picture. So Q is for left to right traversal and stack is for top to bottom. So I would like to give you an example with this one. If this is all these both, for example, you can traverse your BFS. When I say BFS traversal of this particular tree, it will be left to right and you're using Q for that. So the BFS traversal for this will be 1. That is level wise traversal. So one important name for BFS or the breadth first search traversal is also called as a level order traversal. The level order traversal is called as the BFS or the breadth first search. So 1, 5, 2, 4, 3 is your traversal for the BFS because you're moving from left to right level by level. From level 0 to level 2. Level 0, level 1, level 2. And if the same has to be traversed, the nodes have to be traversed following the DFS traversal, then it would be top to bottom. And that will be 1, 5, 2, 4, 3. So it is same in this case because the tree is short. But if you take this, for example, it should be 2, 1, 5, then 4, 3 in DFS. But in BFS, it should be for this tree 2, 1, 4, 3, 5. So you see here the difference. In DFS, you're moving top to bottom. That is why you're making use of a stack data structure. So you are first visiting each subtree basically. You're completing a subtree and then moving on to another subtree. The left subtree and then the right subtree. So basically the parent and then the completing the subtree. You're going to traverse all till the leaf node. You're going to traverse that particular subtree's elements. But on the other hand, in the breadth first search, you're moving level by level, irrespective of your subtree's elements. I hope visually I have made this concept clear to you. Now, once you have understood how we are basically, exploring the neighbors and then continuing in this manner till the queue is empty. Now let us understand how to programmatically implement the NQ, the DQ operations as I was talking about verbally while explaining to you the BFS algorithm. So firstly, to implement BFS traversal, this is what you're just importing, the statement, then public class main. So in public class main, let us I'm creating private int node. This is how a node is basically a vertex. So this is storing the total number of nodes, say. The total number of nodes in the graph is stored in node variable. And then private linked list. I'm basically using a linked list here. I'm just linked list for the adjacency list. As I've told you, you need to first store all your elements of your queue either into into adjacency matrix or adjacency list. But since matrix is n cross n, so it can take the time complexity as order of n square, which may not be efficient or optimal in most of the cases. So in order to reduce your time complexity or to make your program faster, it is recommended to use adjacency list. And adjacency list is nothing but a linked list data structure, which is again a linear data structure. So private linked list integer adj is the name of the adjacency linked list, for example, and the sole purpose of your adjacency linked list is to store all your items or all the nodes of your graph. Then maintaining a queue, you have to maintain a queue basically to where you're going to keep whenever you're visiting each neighbor of your graph. Basically you have to keep them stored. So for storing all the visited nodes, basically you are making use of a queue, and that is to maintain all the visited nodes. Then let us create a method, BFS traversal method. I'm naming it as B. Okay, let us just say BFS for now. BFS method, and passing in as an argument as int v, where v is vertex. V is vertex and nothing but node. I'm just passing as int v, and we can assign. This is how, as you have seen, we initialize variables of any constructor. So, okay, BFS is no, we can since we are initializing the member variables, instead of putting it as BFS, it should have the same name as your main class. So, main class over here, as it is public main, public class main, we have to name the constructor also, which is a method for initializing all your class variables. You have to, it has to have the same name as your class created. So your class, since we are making use of the main now, constructor also should have the same name as the class. We are naming it as main here. The parameter we are passing is int v. Node equal to b is how we are initializing the member variable node. Then adjacency list is created in this way. It is nothing but linked list data structure. So as we have seen that how linked list is created. Linked list is created in this way. With the name adj, which is adj, is equal to new linked list, and assigning it to the number, the length of the linked list. The length of the linked list is given by n here. So n, as I've told, it is the number of nodes. You can just have a note here while you're also taking notes of how BFS is implemented, BFS traversal is done. The total number of nodes basically. So the number of nodes is on nothing but the length of your linked list, number of nodes. You can say the total number of nodes. That is node. And then this is explanatory to you. ADJ is nothing but the linked list. Q is with this data, with this term. Then this is the constructor. Now, once this is done, let us create a for loop here. And we are creating a for loop basically to traverse all the nodes. Now you should start with traversal of all your nodes. So for doing that, int I equal to 0, I your less than b, I plus plus, where b is your basically your parameter you're passing in to the main, and that is assigned to node basically. So node, which is nothing but the total number of nodes. So you're going to traverse from the 0th node to b, the total number of nodes. Then add it to the adjacency list, because initially you have to first store all your items or all your trees nodes. You have to first assign them and store them in one place. So let that place be adjacency list. Adjacency list one by traversing them, you have stored them in the adjacency list. After doing that, you have to place them in queue. So you have created a queue data structure, which is q equal to new linked list. And then after doing this, you can come out of this, basically come out of this main constructor, because this is the constructor you're coming up, because once you have initialized your queue data structure, you have created it after appending all the elements from the given graph to you or given tree to you into your adjacency list. Once that is done, let us create basically a method. We can say we can create a method for inserting. Insert edge basically. If you want to insert any edge, for example, let us create this method with arguments as one vertex and int w. W is nothing but the weight. Now you have to understand that in graph, which I was explaining it to you, each and every vertex is connected to another vertex. May or may not be connected, but yes, it is connected to another vertex, and it is having an edge. An edge will have a value associated with it, and that value is called as weight of the edge. So weight has always to be minimized. Weight, or it can be distance also. When I was saying minimum spanning tree, why it is called minimum? Because the distance, total distance you are traversing, you should ensure that using such algorithms, the distance is minimized to optimize the distance, and the distance is nothing but the value. So whenever you have to minimize the weights totally, total combination of the weights. Weight is nothing but the value assigned to your edge. So let's say that is denoted by W. And in the adjacency list, you are going to add each of them one by one. So adding an edge to the adjacency list, edges are nothing but bidirectional. For example, it can be bidirectional edges also. So you're going to add the edges. It can be bidirectional, or it can be a single directional, or it can be undirected also. Need not have a direction for an edge. So let's say you have inserted this edge and you have added, and while you're adding, this is how you're using, because a linked list to append or basically to insert operation on linked list is done by making use of the add function. So you do it this way, dot add of the element. So making use of this add, then you're going to come out of this function, and now let us create the another function, the function for BFS basically. In this function of BFS, we are going to, this is how you're done BFS, and now you must understand that we have to create a Boolean array instead of like creating a int or like how we usually create any linked list. Instead of that, we have to create a Boolean array, and that is because we are checking whether each and every node is visited or not. So the sole purpose of your BFS is to check to basically to visit all your adjacent nodes. Basically, you're creating a Boolean array for holding the data and to check. So Boolean is basically giving true or false. So in order to check your visited nodes, you're going to make use of the Boolean nodes, Boolean data type. Then int a equal to 0. Store them in this node. Nodes n equal to true. This is the initial value, the default value you're giving. Let's say the node is visited. Whatever node you're visiting in the data structure, let us say it is visited. So you're doing it nodes at n equal to true. Now let us say after visiting your node, what has to be done? You have to add the node to your queue. So you're adding it this way. So basically, I'm writing a comment for you so that you can understand whenever you're coding, you have to understand each line. So root node is added. Basically, you can say root node is added to the queue. And where is it added? To the top of the queue. Because as we know, queue follows FIFO principle. I'm just again revising the concept by writing here. Queue follows the FIFO principle. So you are going to add the node to your queue by doing this queue.add of n. And that is going to be done here. So once you have done this, we have to now loop through it. Like we have to keep appending or adding elements to the queue which are unvisited elements to the queue till your queue size is 0. So how are you going to check that? You can make a loop, while loop, for loop, or a do while loop. Let's say for now we can create a while loop. Then while queue.size not equal to 0. Once you're doing queue.size not equal to 0, over here you have to write n equal to queue.poll. We have seen this method. While I was explaining you queue, I told you what is the function of poll. Poll is basically used to remove your top element of the queue or the front element of the queue. So it is similar to pop in stacks. In stack data structure, you have something called pop. So in queue, you have the poll as the remove method. So remove the top element or top node of the queue. Once this is done, now that you have polled it or popped it out, you have to print the top element. You can do that by making use of the print statement, system.out.print n plus, let's say n plus, yeah, this can be done. Then after that, let us create a for loop basically, and that is to iterate through your linked list and push all your neighbors into the queue. So once you have like removed the top element from the queue, you have to also iterate through your linked list, which is the adjacency list, and then keep pushing all your elements into your queue. So you have a linked list, adjacency linked list, where initially you're putting all your elements and a queue is empty. Initially a queue is empty. Then you're going to keep on pushing your elements of the adjacency linked list into your queue if they are visited. All your non-visited elements, because you have to keep exploring the tree or your graph. So let's iterate that in this way. For int I equal to 0, I less than adjacency at n dot size. Dot size is the method used for any data structure, like especially the list and the queue, linked list or queue, for thus getting the size. So this will give us a size. Like for array, you have, for example, I'm just writing it over here. For array, you have this particular method. Say you have ARR as the array name. Array dot length. This is how you will get a length of the array. Similarly, for strings, you have a different one. And for strings, suppose you have a string name as str dot length with the brackets. This is how in Java you are finding the length or the size of the string. For the array, it is dot length without the braces or without the bracket. For linked list, you are using size over here. Similarly, for getting the size, you have to use size. This is why you are going to iterate. As I've told, you're going to keep appending or inserting all your pushing all your neighbors into your queue. Now, how do we get the neighbors? We are going to get the neighbors by making use of the adjacency list. The adjacency list is storing all your neighbors of your node. So adjacency at n dot get of I, because I is the counter you have maintaining. Then if not nodes at A. After you're doing this, basically you're going to only insert nodes into the queue if they have not been explored already. I'll just write here basically, that is only insert unvisited vertices or unvisited nodes into your queue. You're inserting basically all your unvisited nodes in the queue. All your visited nodes are already stored in your adjacency list, but all the unvisited nodes which are not yet to be explored have to be iterated from your adjacency list and stored in your queue for exploration. So that is what you're going to do here. So making use of the if statement. Now inside your if statement, we can give the logic. So what is the logic? It is nodes at A equal to true. Basically, you're saying that the node has been visited. After visiting your node, you have to also update the value, Boolean nodes array which you have created. You have to also update it to either true or false. But since you have visited the node, you are updating it to true. And then after updating to true, or add your visited element into the queue. Your queue.add of A will add your element into the queue. Once that is done, so we have this over here, we have this braces over here, this and this, it's matching, yes. Now we come out of the BFS. After coming out of the BFS, the last function we are left with is the public static void main, which is nothing but where you're calling all your created functions, user-defined functions you have made, and the constructor as well. You're calling all of them and printing. This is mainly used for getting your output, right? So let us see what was the name of your class. The name of the class was main class. Then let us say we are creating an object of the main class, main graph. Graph is the object, and you're making use of the new keyword to instantiate your object. Then you're making use of the constructor, main constructor. And the constructor will also take a value. It will take an argument. As we have seen the constructor above, it is taking a value. Main is a constructor int v. So v is the vertex of the value which has to be given by the user. Let's just give 6 for now. It is one of the nodes, and it is just taking it can take any other value also. For now, let's say just for initializing, we're taking it as 6. Now, what is this? How do we insert? Basically, we have created insert edge function, right? Now, whenever you want to insert an edge into the graph, you have to make use of the insert edge function which you have created. And an edge is represented by a set of vertices and edges, right? Any edge has 2 vertices. So, it's a pair of 2 vertices, u and v. And u and v are neighbors of each other. So, 0 and 1 are the nodes which are neighbors of each other. So, we have inserted the vertex in this way. Now let's say there is only one there. We have only just inserted one edge u comma v, which is 0 comma 1. Let's keep on inserting. Now how do we do that? Graph.insert edge. Similarly, graph.insert edge. I'm keep on inserting. Insert edge 0 comma 1. Okay, just change it to 0 comma 3. Next line. Then let's say 0 comma 4 is another edge. And then let's say 4 comma 5 is another edge, for example, and 3 comma 5 is another edge. For now, these are all the edges we have inserted into the graph by making use of the insert edge function. Insert edge function is the one we have created here, insert edge. The small function, you can make a note of it, which is inserting your v and w into your, basically the 2 nodes. 2 nodes into your 2 vertices into your graph have to be inserted. and we are making use of the adjacency list to store all your neighboring vertices of the adjacent nodes. So over here, 0 and 1 are adjacent to each other, 0 and 3 are adjacent to each other, similarly 4, 5, 3, 5, 0, 4 are adjacent to each other. That is because there is an edge which is connecting two vertices. Once that is done, we can print the breadth first search, right? Now, how can we print the breadth first search? Over here, we can write BFS traversal of our tree, BFS traversal of the graph, or basically the tree here. Graph is, we can write like this to print. Now, once, in order to do that, how can we basically traverse? There was a function we have used. So we can write BFS function, and BFS function was the function we have created for traversing. And let's say the start element or the source element which has to be provided is 0. As you can see here in the BFS, this is your traversal function, the main function of your code. This is how your BFS traversal is done, and you're making use of the queue data structure. You have to understand here that this is how you are creating your queue data structure, and a Boolean array should be created. And Boolean, the sole purpose of why you're creating a Boolean array is because to check whether the node has been visited or not. You can make a statement here. Boolean. So why a Boolean has to be created, not an int, is because Boolean, because to check if the particular node you have visited is already visited or not, already visited or already encountered or not. Now this is your traversal method. Once this is done, your graph.bfs, then this is how you are done. Now let us execute our program and see what is the output you will be getting. The expected output you should be getting over here, as you can see, BFS traversal of graph is 0, 1, 3, 4, 5. And that is because you're starting over here with 0. So obviously your 0 should be a start node, which you're traversing. Then you're moving to 1 because there is an edge. So your BFS traversal should be 1, followed by 3, then 4, then 5. That is how you're going to traverse. Now you must be noticing that 0 and 3 have an edge. Also 3 and 5 have an edge. So it should be 0, 3, 5. But it is 0, 3, 4 because before visiting 5, already 4 has been inserted as an edge between 0 and 4. So 4 is basically connected to 0, which is our source vertex. So whichever vertex you're starting with, that is given priority. And all the neighboring vertices or the adjacent vertices have to be explored with the priority given to your start vertex. So I hope I have made this clear. In that way only you are minimizing the total distance you have to traverse between two edges, or total traversal for your graph. So I hope I have made the concepts clear for BFS traversal, and this is how exactly the output you will get for BFS traversal of your graph. You can take some time and have a look at the programmatic implementation of each of the methods. The constructor method, the insert edge method for inserting elements into the graph, then your edges into your graph basically, then your BFS traversal, which is your main logic over here, and followed by your main statement where you are actually, the user will be inserting the elements into the graph as edges, and then will be making use of the BFS traversal to traverse all the elements of the graph. Now that you have understood how exactly the BFS traversal is working, let us start with what is DFS traversal of a graph. So DFS traversal of a graph, basically, you have to understand that it makes use of the stack data structure. It is a recursive algorithm. So whenever you see that recursion is taking place, recursion is nothing but calling a function within itself again. So that is where it's a recursive algorithm, DFS algorithm, and it is mainly used to search all the vertices of your tree data structure to explore them. So whenever you want to explore your vertices, if this is the algorithm, second algorithm, we'll be discussing depth first search, DFS. Keep exploring from most recently added node until you have to backtrack. That is the concept of backtracking you have to understand in DFS algorithm. So DFS can be used everywhere. Some of the common examples in LeetCode or any of the programming contests you will come across for DFS is the maximum number of islands, minimum number of islands which are connected to each other. Then you will also have a minimum. You will also have a problem like a coding problem, famous problem like the 8 queen problem. Then you have the chess problem where you have the chessboard, and then you have to calculate the total number of possibilities, basically the possible combinations, where there is a lot of recursion which has to be take place, but recursion will increase your time complexity. So DFS in that way will decrease your, or basically optimize the time and decrease your time complexity by making use of the backtracking concept. And this is very much related to dynamic programming, which is again a algorithmic concept in depth, which is basically used for reducing your time complexities. So this works well with backtracking concept, DFS concept. And the depth first search also starts with the initial node of the graph. So if you see here, it starts with A. It also, like the BFS, it also starts with the first node or the starting node of the graph, which is A over here, the source vertex, and then keeps going deeper until we find the goal node or the destination node with no children. So it keeps traversing from the start, and because of the recursive nature of this DFS, we are making use of stacks. Unlike your queue data structure, which was made use in the BFS traversal, in the DFS traversal, we are making use of stacks because stacks have because stacks are recursive in nature, and also they contain the stack space, which is basically used for reducing time complexity and come handy when you're making use of backtracking. So this obviously the process is this, as you can see here, you're traversing A to C, then followed by A to C to E. Then basically instead of going left to right, as I was explaining you by illustrating with the example, like Q in we are going left to right. So had it been a BFS, you would have gone like AC, then AD and AB, because you're first giving priority to the start node. It's in DFS, it's not like that. You're not going level order. Basically, you're not going level by level. You have to not go to the neighboring vertex, but you have to go to the neighboring vertex of your visited node, the second node. So A, C, E. Then you have to go the visiting vertex of E and not the visiting vertex of A or C. You have to go from E to B over here because there's an edge between E and B, so you have to go to B. Now at the end you have to go to D because that is the only node left and that there is an edge between B and D. This is the difference. So as you can see here, the DFS traversal for this particular graph will be A, C, E, B and then D. A, C, E, B, D. Whereas if you do the BFS of the same graph, it should be A, C, D, B, and then E. E should be visited at the end because it is farthermost, is the farthest from the A or the start node. That is why in BFS that is like that. But in DFS, you're going first visiting, making use of the stacks. You're visiting the instead of the neighboring nodes, you're first visiting the one subtree of the node, basically exploring all the child nodes as well of the particular parent node and the subtree, completing the subtree, then moving on. It's not level wise. So this was an example. This is a DFS algorithm, depth first search algorithm, which is you can make a note of this algorithm for your understanding. So basically marking U, or which is the node, as explored. For each node, this is a for loop. For each edge U comma V incident to U, if V is not marked as explored, do DFS on V. So V is the adjacent node. V is the neighboring node of U node. So you have to do the DFS traversal or explore the V node if V is not marked as explored. But if V is already explored, you need not perform the DFS traversal. Then what is this depth first search? The theorem of that. You have to basically there is no such proof that you have to understand, but you have to basically keep this in mind. What I've told you, that this particular statement, which is a theorem, let T be a DFS tree, let X and Y be two nodes of the tree. So let X comma Y, this is the two nodes of the tree, be an edge that is in G but not in T. Then either X is an ancestor of Y or Y is an ancestor of X in T. This is the theorem for DFS. Then that was all about it, about the DFS. This much will be sufficient for you to understand the concepts about basic DFS concept. Now I would like to show you programmatically to implement the DFS traversal. The same traversal which I am explained you in BFS, it can also be done in DFS way. So you have to basically understand this is the main function, the BFS function. Similarly, I'll be explaining you the DFS with all starting to ending, how it is done. But this is where the main logic comes into hand, the BFS traversal code. So this is mainly used in solving all your competitive programming where you are just, expected to solve only your main logic. Your main logic algorithm has to be solved because all the entire other parts of your program will already be given by default in your problem statements. So coming into your DFS traversal, you have basically like we have to also understand that in the DFS traversal, it can be used to implement something called as topological sorting, which is another applications of DFS you will come into picture while you're solving more and more problems hands-on. And it is some other applications of DFS is to find paths between two vertices, also to detect cycles in the graph, and also, as I was saying, puzzles. There are many puzzles and like solution puzzles to find the chessboard problem and the n queens problem. These are some of the ways where backtracking and DFS come into handy. Now let us implement the code for DFS so that you can hands-on understand. So this will remain same. They are importing all the packages of Java, and then after doing that, let us create a basically a class, public class main. Let us give that name only. Okay, for example, let us say you have. Okay, let us keep it as public class main only because we are making use of the online compiler. Then on doing this, you have to create over here as well a adjacency list, and that is basically to represent all your elements into your of your graph. So basically, be it a BFS or a DFS, the elements should be stored in some place. So let us say it's stored in adjacency list itself. So we are making use of, let us remove private, basically this one we can remove because we would not be needing private int node. So I'm removing this, the total number of node. Private linked list integer edge. This is for creating your adjacency list basically. Then private boolean visited we have to create. Private visit. Let us say we are basically creating a visited array to check whether the nodes have been visited or not. Private boolean visited. Now we have to create the graph. Now to create the graph, we have to make use of the constructor. Main is the constructor int v. Let's say make it capital for understanding. The basically v, which is the number of vertices in the graph over here. It's not the value, it's the number of vertices. So v is number of vertices. You can write here. V is number of vertices of the graph. Then next, coming to adjacency, we have to create the adjacency over here. Now let us do that. Adjacency list. So a list is created this way. New linked list and giving it the size. Size over here is v, which is the number of vertices. And then creating your boolean array visited, and your size of the boolean array can be v as well, which is the number of vertices. Now let us come to creating a for loop in order to iterate over all your vertices so that you can explore. So see, graph is all about, traversal of a graph is all about exploring your nodes one by one after storing them into your adjacency list or adjacency matrix. So we have to store them I plus plus. After doing that, adg at I equal to new linked list. This is how you are initializing. You're like creating the linked list integer type. And after you do this you can come out of the constructor. Basically, now after you come out of this constructor, you have to now add an edge to the graph. Let us use the same function as we did in BFS. You are making use of the insert edge function, which is a use defined function for adding edges to the graph. So add edge over here. Let us change the variable name source for our understanding. Source edge and the destination edge. There is a source which you are starting, destination where you are ending. Then edge, similarly, we can change v and us. Basically v and u only, but I'm just changing it for the naming conventions and renaming them to source and destination. Similar to how we have already created in Q. Now basically in BFS and DFS, you can see they are almost similar, but the main difference between BFS and DFS will come in this particular function. The logic in this function where we are going to make changes. Instead of Q, we are going to make use of stacks. And how we are going to make use of stacks, let us see. Instead of BFS, I'm writing DFS here. Now, instead of n is nothing but vertex only, I will just name it as vertex for our understanding, better understanding. So, same argument, int vertex. That is inserting. So, basically, in this void DFS, which will take your vertex as the argument, you have to now, let me delete all this. Yes. So over here you have to now in the visited array which you have created at the vertex place, you have to write true, and that over here as true. And that is because you're marking the current node as visited basically. Mark current node as visited. This is by default basically. We can say you're marking your current node. Current node is the current vertex here, denoted by visited at vertex. Marking it as true, saying that you have already visited your current vertex. This means your current vertex has been visited. Print it. System.out.print of vertex plus, this will print your vertex which you have visited. Let us make use of the iterator like I was explaining you in the linear data structures. In the case of list, we have made use of iterator in order to see how we can iterate over elements of a list. Now for doing that, let's say it is the iterator object we can create, and whenever you have to iterate over the list elements, you have to make use of the, now here we have named the list as adjacency adg. So let us iterate over the vertices of the list by naming it as adg at vertex dot list iterator. List iterator is the function we are making use of to iterate over the elements of the list. Now while is the, this is how exactly iterator comes into picture, where you are checking whether your particular element which you have visited has any succeeding elements or not. Has next function is used for that, as I've explained. So in n equal to it dot next. Next is for moving forward, basically moving forward to your successive elements. Has next is for checking whether there is a succeeding element or not, and dot next is basically, this next is used for moving to the successive element. Okay, so once this is done, you're storing into the n variable here, n int, and giving the data type as int. Now you're going to check if it is visited or not. If your particular vertex is not visited at n, because visited is the array, and if the nth vertex is not visited, then you have to perform DFS, as we have seen in the algorithm which I have presented in the slides. I have explained over here that basically in this algorithm, if V is not marked as explode, then perform DFS. But if it is marked as explode, then just mark U as explode, and you need not follow any logic, any code. So basically over here also, if it is not visited, then DFS is performed. Otherwise, DFS is not performed. Okay, you can just simply come out of the while loop if all the nodes have been visited. But if any node is left and yet to be visited, perform DFS as well. After performing DFS on that, come out of this DFS function. And now after coming out of DFS function, only function left is main function. That is similar to how we have done for the BFS. In the BFS, we can just, we have initialized with 6. Let's say we can do it with 8 or any value. Then graph.insert edge, inserting 0, 1. Let's keep it like this, 0, 3. And let's say, let's change a bit and check what the result will be. And then 2, 4. Why we are just inserting random values, and yeah, 3, 5, let's okay. Then just instead of BFS, since we are printing DFS traversal of the graph, then graph.dfs is the function, the name of the function we have created, and that is our main logic. The source vertex is 0, that is same as the BFS. So you can see here that all the other functions we have created apart from the DFS function, other functions are almost the same, only the naming conventions I have changed. Naming conventions I've changed, like source and destination instead of U and V. Then I've changed, instead of like a different name was given, I've changed it to visited vertex, which is again a Boolean array. So only the naming convention has been changed. So, okay, Boolean visited. It's not visited, it's visited. So apart from that, everything is same, but only the DFS is the main logic, the function we are changed. DFS, where we are making use of something called as iterator here, and that is because we are iterating over every element of the list, adjacency list. And you have to understand the concept of backtracking also. Backtracking is used here because it is using this not condition. So it is basically checking if it is visited or not. If the node or the vertex is not visited, then perform DFS. Otherwise, backtrack. That is, otherwise don't perform anything, and again iterate over the next element. So this has next is the function which is nothing but doing the backtracking part here. Backtracking. Backtracking for DFS is done and handled by this logic of yours in the while statement. I hope I have made this concept of DFS clear to you. And let's see, public class main. There is a error. Yes, we have to have a brace over here. Public class. Let us see if we have the sufficient braces. Yes. Now, on running this, you will see the DFS traversal. Error cannot find symbol. Variable I class main. Let us see where it is, 11th line. So over here, in the main, the constructor over here, for int I equal to 0, I is less than b, I plus plus. So cannot find symbol, variable I. Okay, so it has to be int I, not I, just int I, and that's it. It will run. Yes, as expected, our DFS traversal of the graph is 0, 1, 3, 5. And why is it 0, 1, 3, 5? As you see here, we are first starting with 0. So as expected, 0, then 1, then 3, and then 5. Now you must be seeing that there is no 4 present here, right? Although there is an edge between 2 and 4, there is no 4 present at all. And that is because 2 is not even having an edge or a connection. 2 is not having any connection between, there's no edge basically between 1 and 2. So how can we assign 2 and store it? It is not even traversing. So that is why. So suppose if instead of 2, I have changed it to 1. Let us see whether 4 will be printed or 5 will be printed. As you see, DFS will be giving us 0, 1, 3, 5, 4. 0, 1, 3, 5, 4. 4 is printed at the last. Although we are giving, in BFS, we started with give priority to 0 and level wise started. It was mostly in the increasing order as you saw in BFS, because it gave it, if it's BFS, it should have been 1, 3, 0. It should have been starting with 0, then 0, 1, 3, 4, 5. Because adjacent to the most nearest to 1 instead of 5 is 4. But on the other hand, in DFS, it is not checking or giving priority to starting source vertex. Rather, it is checking whether all the nodes have been explored or not. And that too, we are going to explore it top to bottom, or we can say the subtree wise. So if you start with 0, then 1, then once the adjacent node of 1 is 3, which is going to be coming here. Adjacent node of 3 is 5. So that is why 5 has to be coming. We are not going to take adjacent node of 1. Since 3 was the last visited vertex after visiting 1, the corresponding adjacent vertex of 3 has to be come here, which is 5, followed by 4, which is a leftover vertex. I hope I have made this concept of DFS traversal very clear to you. And now that you are unable to understand what is DFS algorithm, basically the complexity. Also, we have to understand basically one important topic I have to cover is time complexity. Since time complexity I've also explained in the theoretically and also with examples in depth how to calculate time complexity and space complexity. What is the time complexity of DFS and BFS? I would like to explain it to you now. Basically, DFS and BFS, both of them will take order of V plus E as the time complexity. Now, what is V plus E? V is number of vertices or nodes and E is the number of edges. So, order of V plus E is the time complexity of BFS and DFS. That is the time complexity you have to remember. Now, basically, to summarize, we have seen that what is graph. So it is basically having vertices and edges, and that is represented by a pair of V and E. Then you have the number of vertices as absolute number of B, and then the value of the number of edges is given by M over here. These are just some of the notations we are using or symbols for demonstrating. Then neighbor, incident, cycle, path, connected, what is a tree. We've also discussed what is BFS and DFS, which are nothing but two approaches to traverse a graph. So as we have seen in tree traversals, there were three different types of traversals as we have seen in order, pre-order and post-order in the illustrations. We have over here, we have seen what is BFS and DFS traversal, how to programmatically implement DFS and BFS traversal by creating functions and also the main logic in Java. And then in BFS in short, which is nothing but broad tree. So whenever you have a broad tree, as the name says, breadth first search. So it's nothing but, in short, the short broad tree or a bushy tree is nothing but where you're using a BFS. So it is to traverse a graph. These both are basically graph traversal techniques to process each node of the graph, and each of them are producing a tree only. So when we see the output of the BFS of DFS function, both of them gave us a tree like structure. So tree out, both of them are producing trees, but then the tree produced by BFS is going to be short and a broad tree. It is having a huge breadth and it is short in size. Whereas DFS, as it uses stacked data structure, it is, and not left to right traversal, it is going to produce a deep narrow tree which is long or more height, long in length, or a scraggly tree. So that was all about it, about graphs, BFS, DFS traversals, and that is the end of your data structures and algorithms concepts, which you have understood. Basically, what are DSA, how important they are, what is linear data structure, the classification, time complexity, space complexity, what is a non-linear data structure, the different types of non-linear data structures, trees, types of trees, what are the key terminologies you have to be aware of, some of the minute functions you have to be careful, like size, and we have seen has next. Then we have seen the different functions which differ for linked list, queue, stack, how they differ for different types of trees also, and when a tree cannot be called as a graph, and graph, what is the difference between a graph and a tree, basically the applications of graphs and trees, and ended with BFS and DFS traversals by seeing the programmatic representation along with the time complexity, which is order of B plus E. I hope I have made the concept of data structures very clear to you, and now if, you have understood and have a good fair understanding, especially programmatically in Java language, where you have come to understand how they can be leveraged. If you have any doubts, please drop them in the comments, and I hope you have a good day and happy learning. Thank you.